Welcome back to the Deep Dive. We're here to break down the dense technical papers so you don't have to. Today, we're looking at something pretty exciting from DeepSeek AI. It's called DeepSeek-OCR, and it tackles a really big problem using vision language models, or VLMs, in a novel way: context's optical compression.
That's right. It's a really interesting approach.
Now, if you're working with large language models, especially deploying them, the absolute pain point, context length. Processing really long text sequences is just, well, it's incredibly computationally expensive. It scales quadratically.
Yeah, that quadratic scaling is the killer. Double the context, and you could quadruple the compute and memory. It hits a wall fast.
Exactly. It's what stops us from having these, truly massive long-running contexts in a practical sense.
And DeepSeek-OCR aims to sort of sidestep that whole problem. The core idea is deceptively simple. Use the visual modality, an image, as a way to compress text information before it even hits the language model.
Okay, wait. That sounds backwards. We spent years turning everything into digital text for machines. Now we're taking text, making it an image, feeding that to a VLM, then decoding it. How does that save tokens?
Right, it seems counterintuitive. But think about a high-res image of a document page. It holds tons of information, text, layout, structure. But visually, you can represent all that using way fewer vision tokens compared to the raw text tokens.
Okay, so a page might be, say, 3,000 text tokens.
Exactly. But maybe only a few hundred vision tokens represent that same page as an image. That's the optical compression. And DeepSeek-OCR uses two main parts to do this. There's the DeepEncoder, which is the engine handling the image and compression, and then a specialized decoder, DeepSeek 3B MOE A570M, which takes those compressed vision tokens and turns them back into high-quality text via OCR.
Got it. So our mission today, really for you listening, especially if you're developing or deploying these systems, is to dig into that DeepEncoder. We want to figure out how much compression you can realistically get away with while still keeping things accurate and usable. Let's dive into the DeepEncoder first. Why build a new VLM encoder? There are good open source ones out there, right? Like Very, Intern VL 2.0, Qwen2VL.
Yeah, that's a fair question. It really boils down to resource management, especially activation memory. Existing VLM encoders, even the good ones, tend to struggle with the kind of high-resolution document images you need for really accurate OCR and deep parsing.
How so? What's the specific bottleneck?
Well, some models, when they see a big document image, their activation memory just explodes. You get GPU overflows immediately on typical hardware. Others might avoid the overflow, but they do it by generating thousands and thousands of vision tokens to capture all the detail.
Which defeats the whole point of compression.
Exactly. And it slows inference way down. DeepSeek needed something that could handle high-res input without the memory blowing up and without spitting out too many tokens.
Okay, sounds like a tricky balancing act. How do they architect DeepEncoder to manage that? Fine detail plus global structure, but keep the GPU happy.
Neural signal check. DeepEncoder's technical design. So the DeepEncoder itself is about 380 million parameters. They designed it pretty cleverly as a serial pipeline, tackling complexity step by step. It basically combines two main stages. First, there's a visual perception component. This uses SAM base, about 80 million parameters, mostly using window attention.
Window attention. So that's good at picking out the local details, like little text boxes, lines, that sort of thing.
Precisely. It finds all the fine-grained stuff. Then second comes the visual knowledge extraction component. This one's bigger, built on CLIP, large, around 300 million parameters. And this part uses dense global attention to understand the overall page layout, the context, how all the little pieces fit together.
Local details first, then global understanding. But hang on, that first stage must create a lot of intermediate data capturing all those details. If you feed all that straight into the big global attention part, wouldn't you just run into the same memory problem?
You've hit on the key piece. Yes, that would happen. The absolute crucial element is what they put between those two stages. There's a 16x convolutional compressor module sitting right after the SAM base part and before the CLIP large part.
The 16x compressor? Okay, that sounds significant.
It's essential. It manages the data load before it hits that expensive global attention mechanism.
Can you give us some numbers on that? Like, how much difference does that compressor actually make?
Yeah, let's take a standard example. Say you feed in a 1024 by 1024 image. The first part, the SAM base, might generate something like 4096 patch tokens, capturing all the local detail.
4096 tokens. Okay,
Yeah.
Feeding that into a 300 parameter global attention model sounds...
Bad. Very bad for your GPU memory. But the 16x compressor jumps in and downsamples that dramatically. It takes those 4096 tokens and crushes them down to just 256 tokens.
Wow, okay. 16 times fewer tokens hitting the expensive part.
Exactly. That's how they keep the activation memory manageable, avoid the overflow, but still retain enough information for the global part to understand the document structure.
That's a really smart design for efficiency. And they paired this efficient encoder with the DeepSeek 3B MOE decoder. Why that specific one? Mixture of experts, right?
Yeah, the MOE architecture, specifically the version activating 570 million parameters, is all about inference efficiency. It basically lets them get the quality and expressive power you'd expect from a much larger, say, 3 billion parameter dense model.
Right.
But with the inference speed and resource footprint closer to a much smaller, like 500 million parameter model, perfect for high throughput OCR.
Makes sense. Okay, let's shift gears slightly into segment 2. We need to nail down this core question for anyone thinking about deployment. What's the limit? How far can you push this compression? How few vision tokens do you actually need to reliably decode end text tokens? Where does it break?
Right, the crucial trade-off. They did a specific study on this, the vision text compression study, using the Fox benchmark, to find those boundaries. And they found a pretty clear point for what they call near-lossless performance.
Okay, what does near lossless look like in terms of numbers?
When the compression ratio is around 10x or less, for example, taking 900 to 1,000 actual text tokens and compressing them down to just 100 vision tokens, the OCR accuracy stays really high, like around 97%.
10x compression, 100 vision tokens, 97% precision. That sounds pretty good for high throughput.
That's definitely the sweet spot if you need maximum quality.
But what if you're really constrained on tokens? Maybe for cost or latency reasons. Can you push it harder past 10x, like 15x, maybe even 20x?
They tested that too. When you get closer to a 20x compression ratio, they looked at it compressing 1,200 to 1,300 text tokens down to only 64 vision tokens. The accuracy does drop noticeably. It falls to around 60%.
60%. Okay, so that's a significant drop. Clearly hitting a wall there where information is just getting lost.
Yeah, it suggests you've gone too far. The visual representation is likely getting too blurry at that level of compression to reconstruct the original text accurately.
But here's where it gets fascinating conceptually. The paper doesn't just say 60% is bad. They actually speculate about this information loss.
Right. They suggest framing that degradation, that blurriness from extreme compression, as potentially mimicking a biological process.
Like human memory.
Exactly, like a memory forgetting mechanism. Think about how your own memory works. You remember recent conversations pretty clearly, but stuff from weeks or months ago, it gets fuzzier. You remember the gist, the main points, but the exact wording fades. You lose fidelity.
So by compressing the visual context so much that it loses detail, it's kind of like the model is forgetting the specifics but keeping the overall meaning.
That's the idea they float. It's a way to retain long-term context without needing perfect recall of every single token from the past, which, as we said, is computationally prohibitive.
Which loops right back to our initial problem. If you treat older context as these highly compressed, slightly blurry images instead of raw text tokens,
you could potentially handle much, much longer histories without that quadratic scaling blowup. It's a really provocative idea.
Definitely. Now, practically, documents aren't all the same size. How does DeepEncoder handle different input resolutions, especially really big ones?
Good point. They built in flexibility. There are fixed native resolution modes, tiny, small, base, large for standard sizes. But for really big stuff like engineering drawings or newspaper pages, they have dynamic resolution modes called Gundam and Gundam M.
Gundam mode.
Yep.
Okay, how does that work?
It uses tiling. Instead of trying to process a massive image all at once globally, it breaks it into smaller tiles, like maybe several 640 by 640 patches. It processes these local tiles and combines that with information from a downsampled global view, maybe 124 by 124.
So it gets both local detail from the tiles and overall structure from the global view.
Exactly. And crucially, you can control the number of tiles, usually between 2 and 9. This lets you handle very high-res inputs.
While still controlling the final output token count, because it's based on N, that's important for planning resources.
Precisely. Predictable token output, even with variable, large inputs.
Okay, let's pivot to segment 3, enterprise value. Efficiency is great, but how does DeepSeek-OCR actually perform against established players? You mentioned benchmarks like Omnidoc Bench, comparing it to models like Miner U 2.0 or GIOT OCR 2.0.
This is where the benefits of optical compression really shine in practical terms. The efficiency gains are quite dramatic. Let's take a common scenario. DeepSeek-OCR in its small mode uses just 100 vision tokens.
Right, the near-lossless one we talked about.
Even with only 100 tokens, it outperforms the IoT-OCR 2.0, which needs 256 tokens to get similar results.
So less than half the tokens for a better performance. Nice.
But the gap gets really wide on high-resolution tasks. DeepSeek-OCR in Gundam mode, using fewer than 800 tokens, beats minor U 2.0, which often needs close to 7,000 vision tokens to handle the same kind of complex, high-res page.
Well, hang on. Say that again? Under 800 tokens versus nearly 7,000?
Yep. Fewer than 800 versus almost 7,000. For comparable, state-of-the-art results on challenging documents.
That's nearly a 9x reduction in vision tokens per page. For anyone listening who manages cloud compute budgets, that's huge.
It's a massive difference in operational cost and throughput potential. And it has big implications for another area, creating training data for LLMs.
Ah, right. If you need to process millions of documents to build a dataset, that efficiency matters a lot.
Absolutely. The paper actually gives some throughput figures for this data generation use case.
What kind of scale are we talking?
They state DeepSeek-OCR can process documents for LM-VLM training data at a rate of 33 million pages per day.
33 million pages a day.
Per day. That's using a setup of 20 nodes, each with 8 A140G GPUs. So if your job is building massive multimodal datasets fast, this kind of tool could be a game changer.
Unlocks serious scale. Now, beyond just pulling out text accurately, you mentioned deep parsing. What does that mean in practice? What kind of complex structures within a document can it understand?
Thanks to the training data, it's not just doing basic OCR. It understands document structure via a single prompt. It can handle things embedded in the page. For example, it can look at charts or complex tables and parse them directly into structured HTML table format.
Useful. What else?
It can recognize chemical formulas and output them in the standard SMILES format. It can even identify and structure simple geometric figures drawn on the page.
And languages. Does it handle multilingual documents well?
Yes, that's another strength. It supports nearly 100 languages found in PDFs and images. And it can output the text, either respecting the original layout or just as a clean text stream, depending on what you need. Very versatile for global operations.
We are wrapping this up then. The big takeaway seems to be that DeepSeek-OCR makes a really strong case for this idea of context optical compression. It delivers significant token reduction anywhere from, 7x up to maybe 20x at the extreme end.
Right.
While hitting state-of-the-art efficiency and accuracy on real-world OCR tasks, plus enabling massive data generation.
I think that's fair. It shows the visual modality can be a very effective token compressor. But for me, the really profound implication is that connection to memory we discussed. This idea of letting older context become blurrier by compressing it more, mimicking how human memory fades. That feels like a genuinely new way to think about managing context in AI.
It really does. Which leads us perfectly into our final provocative thought for you, the listener, to chew on. We've seen DeepEncoder prove that visual modality can be a powerful token compressor. So, could future AI architectures take this further? Could we use this optical compression technique not just for documents, but for managing, say, dialogue history in chatbots, going way beyond current sequence length limits? Imagine an architecture that keeps the very recent conversation as sharp text, but progressively optically compresses older parts of the dialogue history into these compact visual representations.
Dynamically managing the resources based on how old the information is.
Exactly. Could this be a path toward theoretically unlimited context? A way to finally break free from that quadratic scaling bottleneck by selectively forgetting details, just like our brains do.
It's a fascinating possibility.
DeepSeek-OCR certainly suggests the foundation is being laid.
Something that's made to think about.
Thanks for tuning into this deep dive. For more technical breakdowns on AI and ML, check out our website, neuralental.org, and find us on YouTube. We'll catch you on the next one.